Okay, so this is for my grade 11 applied math students. This is the second part of the 7.5 lesson on using factoring to solve quadratics. And before we go any further, I'm going to point out that on yesterday's lesson I made a boo-boo. See the problem with the first one? Negative 6 times 1 is not plus 6. Can you go back in your notes and make that a minus like it's supposed to be? That's what it was supposed to be. I wrote it down wrong. My bad. I'm looking at my notes. It's negative 6 in my notes. I don't know why I wrote a plus 6. Temporary insanity is what I will plead. Now that question works, right? Because negative 6 times 1 is negative 6. And when you FOIL that out, negative 6x plus 1x would definitely be negative 5x. So yep, that example is correct if you go back and fix that, change that plus to a minus, would you? Silly me. Okay. We left off a little later than that. We did some more solving for x, doing some factoring, and I left you with this one to try for yourself, using what I call the decomposition method. It's like, well, why can't you just open up two brackets and figure out that, you know, this is, say, 6x and this is 1x? Well, remember, that's not the only way to make 6. 6x and 1x could be the right answer, but could also be 2x and 3x. And then on top of that, negative 12. Think of all the ways you could break up negative 12. Negative 1, positive 12, positive 1, negative 12. Negative 2, positive 6, positive 2, negative 6. Negative 3, positive 4, positive 3, negative 4. Phew. And then I have to figure out which of those pairs matches up with which of these pairs. Too much thinking. Instead, you say to yourself, you go back to what I was doing here. Let's see. No, you don't go back to there. You go back to what I was doing here. You say to yourself, if I had something like, say, 3x plus 4 and 2x minus 3, if you multiply that out, 3x times 2x is 6x squared. 4x times 3 is negative 12. And in the middle, you get 3x times negative 3, which is negative 9x, and 4 times 2x, which is plus 8x. And then those two things add up to make minus x. So there it is. There's the two factors I'm looking for. Now, how did I know that this should be what I should pick? Well, here's what you actually know. This is something that's always true. If you take a second to look at this line before you add these two guys up, notice that 6 times negative 12, 6 times negative 12 is negative 72. Notice also that negative 9 times positive 8 is also negative 72. And that will always be true when you multiply two binomials with the same kind of terms in them together. You will always get two outside numbers that multiply to make the same thing as the two inside numbers. So let's pretend now like I don't know any of this. Move over. Or here, let's just erase it all. Let's pretend like I didn't do any of this. You didn't see anything. That never happened. And while we're at it, let's get rid of all this. Blah, 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 blah. Let's get rid of all that. Okay, so pretending like I'm just starting over with this example. What is 6 times negative 12? Well, it's negative 72. Now I ask myself, I say, self, what two numbers times to make negative 72 that would add up to make negative 1? In other words, what numbers times to make 72 and they're only 1 apart? And if you know your times tables, you go, oh, well, 72 is 8 times 9. They're 1 apart. So this would be minus 9 times plus 8. And now we call this decomposition because what I'm about to do is I'm going to take this term and I'm going to decompose it into these two terms. And then I'm going to do what's called partial factoring, which is good because that's what our lesson is going to do later. We're going to factor 3x out of here, these two terms, leaving behind 2x minus 3. These two terms have a 4 in them. I'll factor that out. It leaves me with 2x minus 3. And if you're doing this right, you'll notice the two brackets always end up being the same thing. And then you factor the bracket out of the question, and that leaves behind 3x plus 4, and that's how you do it. So now solving, I'm not done yet. That's my two factors. 2x minus 3 is 0, so 2x equals 3, so x is equal to 3 halves. And 3x plus 4 is equal to 0, so 3x is equal to negative 4, so x is equal to negative 4/3. So there we go. There's my two solutions to the quadratic equation. Isn't that nice? So that was the example I left you with to see if anybody could actually get it. If you like decimals more than fractions, okay, you could give me the answer in decimals, but do notice, problematically, what kind of a decimal do you get when you have thirds? Yeah, it's going to be repeating, right? 0.3. So this would be like negative 1.3 repeating. That's why we usually like fractions better. Okay? All right, like I was saying, I was going to do this example, and I already have it written out. I'll make up a different one. Suppose we have, let's see. I guess I did that one last semester. Let's see, where's the rest of my examples on? Here we go. There's the next one. Jot that one down. I stole this one from your textbook. What are the two values for p in that equation? 75p squared minus 192. Okay, this one's a little different than the last example. This one I'm going to notice that both of these numbers here have 3's in them. Do you remember how to tell if a number is divisible by 3? All you have to do is add up the digits. 7 plus 5 is 12. 1 plus 9 plus 2 is 12. 3 goes into 12, so 3 goes into those two numbers. So if I divide both sides of the equation by 3, I get 25p squared minus 3 goes into 18 6 times, carry the 1, 64, and 0 divided by 3 is still 0. And does that look familiar? What do you notice about those two things? These things are perfect squares. So this one is a difference of squares. And then once again, I can say 5p plus 8 is 0, or 5p minus 8 is 0, which means 5p is equal to negative 8, p is equal to negative 8/5, 5p is equal to positive 8, p is equal to positive 8/5. When you write your answers for a question like that, I don't mind if you combine them into one answer and just say that. Technically, that's saying two answers. So there's that example. That's a nice one. Difference of squares. Let's see if I can find another one that uses decomposition. Or else, if not, I'll have to make one up. There we go. That's a decomposition. Well, it doesn't have to be, but I'm going to make it one. Solve and verify the following. Okay. This one's pretty gnarly. Actually, I don't know that I need to do decomposition on this one. You know what I noticed about this one? 4x squared is a perfect square. It's 2x squared. And 49 is a perfect square. It's 7 squared. And if I take the square root of 4x squared, which is 2x, and I take the square root of 49, which is 7, 2x times 7 is 14x, doubled is 28x. This one is a perfect square trinomial. Neat. So that means that it's actually 2x plus 7 squared. And if that equals 0, let me make my pen a little bit wider. There, that better? I like that better. So now I can square root both sides. And remember that when we hit the point algebraically where we square root both sides of the equation, we usually get a plus or minus. But we don't do that here because there's no such thing as plus or minus 0. The square root of 0 is just 0. And then 2x equals negative 7. And the answer for this one is x equals negative 7 halves. So there's another example I stole from your textbook. Could I have done this one by decomposition? Yeah, I could have. It would have been kind of hard, though. 4 times 49. Ooh. 4 times 50 is 200, so that's 196. Quick, what two numbers times to make 196, but if you add them, you get 28? I don't think I know that off the top of my head. But actually, you know what? It would actually be 14 and 14. So if you tried doing it by decomposition, you'd get this. Haha. And then you can factor out 2x from the first two. And you can factor out 2x from the second two. And look at that. That works out real nice. Then you can factor out, hang on a sec. No, you can't factor that out. You can factor out 7. That's what I meant to say. 7 from the second two. And then you have 2x plus 7 times itself. And that gets you back to same places here. Neat. So you could have done that one by decomposition if you'd wanted to. Okay. On the loose leaf you're working on, we need kind of a new title. And the title here for this section of our notes is going to be Find the Vertex of a Quadratic from standard form. And this gets to a question that somebody asked yesterday. They said, well, what if you try to factor it and it doesn't factor? Like, for example, example 1 for this little section will be this one here. And again, I'm stealing this one right from your textbook. Your textbook has this example too. That doesn't factor. Because, quick, what two numbers times to make 10 and add to make 6? Well, 10 is just 2 and 5 or 1 and 10. Any of those things add up to make a 6? No. So it doesn't factor. So what I'm going to do, notice this one's not asking me to solve the equation. It's trying to find the vertex. So that gives me a little bit of leeway. I don't have to worry about what the actual x-intercepts are. What I'm going to do is I am going to factor just this part of it. This is called partial factoring. I can factor a negative x out of these two things. And I would get negative x minus 6 in here, and plus 10. And then I'm going to let each of these two factors equal 0. And that's going to then be negative x equals 0, which means, well, divide both sides by negative 1, so x is 0. Or negative x minus 6 equals 0, and again, divide both sides by negative 1 if you like. And x plus 6 equals 0. So x equals negative 6. And then once I have those two x values, I'm going to plug them back into the original equation and find the y values. So if x is 0, y would be negative 0 squared plus 6 times 0 plus 10. Well, that's actually really easy. Y would be 10. So if in this equation here, if x is 0 when y is 10 or y is 10 when x is 0, I can say it has the point 0, 10. And for this point here, when x is negative 6, this one takes a little more thinking. I have the negative of negative 6 squared plus 6 times negative 6 plus 10. And notice that that's going to be, let's see, negative 6x plus 10. So that's going to be negative 36 minus 36 plus 10. Okay, hang on. I think I might have goofed something up here. Yep. Maybe you speed where I've goofed up. No? Okay. Yes, I did goof up. My bad. When you factor a negative out of itself, it's positive. That's the mistake. Can you fix that? I need more coffee. So this should be positive 6, which makes that positive 6, which makes that positive 6. There we go. Get rid of those extra negatives. There we go. That's what's supposed to happen. I knew something was going wrong because I knew the way this is supposed to work out. These two numbers, of course, make 0, and then y is equal to 10. So if x is 6 when y is 10, I have the point 6, 10, and now I'll bet you know how we find the vertex. If I have a parabola, and it's got 2 points on it, one of them is at 0, 10, and the other one is at 1, 2, 3, 4, 5, 6, 10. What do I know about the parabola? The parabola must have a vertex exactly in the middle. So the x-coordinate of the vertex, also known as the axis of symmetry, would be halfway between 0 and 6. Now again, that's an easy one. Halfway between 0 and 6 is obviously 3. But if you had numbers that were harder than that, what's the quick way to figure out the middle of two numbers again? Right, add them up and divide by 2. So there we go. So the axis of symmetry is x equals 3. And then go back to the original equation, and if x equals 3, then y would equal negative 3 squared, right? Because remember, the original equation was y equals negative x squared plus 6x plus 10. So negative 3 squared plus 6 times 3 plus 10. Oops, 10 I says. There we go. That looks like a 16 now. 10, that's better. So that would be negative 9 plus 18 plus 10, which is 9 plus 10, which is 19. So therefore, the vertex is 3, 19. So there you go. You can find the vertex even if you're in standard form, even if it doesn't seem to factor. Okay, we got a question. Why did we factor out? Because we can't factor the whole thing. The question is, why did we factor just this part? Well, we can't factor the whole thing. I can't think of two numbers at times to make 10 and add to make 6, right? Oh, would it have mattered? The question is, why factor out negative x? Because it actually led me to goof it up and make a mistake. But why not just factor out x? Okay, if I'd have done that, if I'd have just factored out an x, notice that I got the same answers. If I set this to 0, x is still 0. If I set this to 0, negative x plus 6 equals 0, and x is still equal to positive 6. So it doesn't really matter which way I do it. Okay, notice both of these answers get arrived at either way. Okay? So there we go. So there's how you find a vertex from a standard form, even if you can't factor it. If you can factor it, well then great, you know the x-intercepts, and again, your axis of symmetry is halfway between them. But notice, these 2 points aren't x-intercepts. They're somewhere up on the parabola. But I know that they are the same height, which means that the parabola has to exactly get cut in half between those points by the axis of symmetry. So that is a very handy little trick, and there's a few questions in your homework that's coming up that ask you to do this. In fact, maybe I'll just do one of them with you. Let me grab it from the book. Let's see. This is 7.5. I'll just do one of your homework with you here, just to show you one more example. Here we go. Use partial factoring to determine. Okay, so how about this one? Let's find the vertex. So we'll call this example 3. Are we on example 3? I've lost track. Find the vertex of, let's do this one. Ooh, let's do this one. It has a fraction in it. F of x equals negative, oops, my pen's being strange. Negative 1/2 x squared plus 2x minus 3. Quick, what two numbers times to make let's see, negative a half times negative 3 would be plus 3 halves. What two numbers times to make 3 halves but add to make 2? I can't do that in my head either, so I'm not going to try factoring the whole thing. What I'm going to do is I'm going to do my partial factoring. So partially factored, I'm just going to factor those two things. I can take out negative a half x, and that would leave behind an x. Now careful here. If you factor a half, first of all, if you factor a negative out of a positive, you know it leaves a negative. That part's easy. But if you take a half out of 2, almost everybody's going to go, oh, it's 1, right? Because half of 2 is 1. But remember, you're factoring something out. It's like you're dividing it away. 2 divided by a half is not 1. Ask yourself this question. What number goes here so that if you multiplied this by that, you'd get this 2? Half of what number is 2? 4, right? This is x minus 4. And then once again, the next step on this is take your two factors and set these to equal 0. So negative 1/2 x is 0, so x is just 0. And x minus 4 is equal to 0, so x is equal to 4. And then you know that your vertex has to be halfway between 0 and 4. So your vertex has to have an x coordinate of 2. And then from there, go back to the original equation and figure out what f of 2 is. So I have negative 1/2 times 2 squared plus 2 times 2 minus 3. A half of 4 is 2, but it's negative, plus 4 minus 3. Negative 2 plus 4 is 2. 2 minus 3 is negative 1. So 2, negative 1 is the vertex. Isn't that nice? We call that partial factoring. All right, I'm going to do one more example with you before I turn you loose in your homework. This is called applied math, and geez, for the last 2 classes we've been doing everything kind of theoretical here. Let's do an actual word problem. This is a neat problem. I like this problem. Again, it's from your textbook. And where did I put it? I put it on this page somewhere. Did I put it? Where is it? Hold on. There it is. It's over here. I'm going to just pick it up and move it. Yeah. And then we'll make things bigger. Okay, here we go. The entryway to the main exhibit hall in an art gallery is a parabolic arch, like so. Okay? And there's an equation that models the shape of this arch. There's the equation. Now, several sculptures are going to be delivered to the exhibit hall in crates. Each crate has a square-based bottom, and it's 7.5 feet high. And the problem is, I didn't copy the actual problem. Well, the problem is, what's the actual maximum that this width could be to fit through the doorway? In other words, will this crate fit through that space? And that's the problem. Question? Oh, I don't remember what page in the book this actually is. If you want to take a look at the way the book does it, $3.99. Again, we'll probably get a copyright strike now because I actually said the name of showing you a picture from the textbook and I told you what page it's on. Oh well, if it happens, it happens. All right, moving along. What do I do to figure this out? So if this is 7.5 feet high, will that actually fit in the parabola? So basically, I guess what I want to know is, if this is 7.5 feet high, how big is this? What's the absolute biggest that it could be so that it would fit? Okay, so let's take a look. How are we going to solve this? Well, what would be useful would be to figure out if this is the vertex, it would be useful to figure out what these 2 points are. how far apart are these would be the useful thing to do. Okay, so let's take a look at the formula. The formula is, again, height as a function of width is negative 0.625 w squared plus 5. Okay, so what I'm going to do is I'm going to say, all right, this height here has to be 7.5. So when this height is 7.5, how much is W? Oh, I lost my W. There, W. Okay, when you're solving a quadratic, you move everything to one side. So I'm going to move these two terms to the left side. So I'm going to add them. So I'm going to add this one. And I'm going to subtract that one. And if I've left everything off of this side, now it's 0, and aha, this is now the same stuff we've been doing. Can I solve that equation? Now you might look at that and go, well, I don't know that I want to factor it. Probably not a good idea. But you know what I am going to try to do? I'm going to try to get rid of this number. I'm going to divide both sides of the equation, which means all of its parts, by 0.625. On the right side, it's nice and easy. 0 divided by anything is still 0. And believe it or not, use your calculator. Let's see if I can get my calculator to open. There it is. Use your calculator, and you'll see that, well, on this side, it's just going to be w squared. But 5 divided by that decimal actually is a whole number. 5 divided by 0.625, very nice, is a whole number. It's 8. And then 7.5 divided by that decimal is also a whole number. It's 12. Hey, look at that. That's one I can factor. What two numbers times to make positive 12 that add to make negative 8? And it would be negative 6 and negative 2. So W I says. So W equals 6 and W equals 2, those are supposed to be W's, are my two x-intercepts. So basically, if I were to look at the graph again, here's the graph. This is a 2 and this is a 6. Or actually, sorry, that's not what I meant to do. My bad. Oh yeah, that's right. Yeah, this is a 2 and that's a 6. Actually, no, that's not right. There we go. The box is in here. There we go. The box, the box, the box, the box. There. This would be a 2. Oops. 2. And this would be a 6. So, right, when x is 2, y is 7.5, and when x is 6, y is 7.5. So now I can find how wide this is. What's the answer? How far is it from this point to this point on this picture? The answer is 4. Therefore, the maximum width is 4 feet. Anything wider than 4 feet, and the box won't fit through the door. I guess the argument could be made that even if it was exactly 4 feet, it might get wedged in there. But how about this? It has to be less than 4 feet wide. How about that? Okay, that one you're probably looking at going, oh, I wouldn't have thought to divide by this decimal. Chances are, if I give you a problem like this, I will allow you to use Desmos. And if you'd have used Desmos to graph this thing, let me get Desmos up here again. There he is. If you were to graph the original equation, which was, again, h of w equals, and what was it again? Negative 0.625, negative 0.625 w squared plus 5w. There's the thing. You might be asking yourself, okay, well, how would I figure this out? Well, I need to know where the height is 7.5. Now, you can try to just move your cursor until you get to 7.5 for a height, which is kind of hard there. It's 7.599. Oh, there you go. Oh, I just hit it. But you know, the easier way to do it is to just make a line where it's just height equals 7.5. And oh wait, I guess it doesn't like me using h. You know what? I guess I'm confusing it. I'll just stick to y and x. Y and x. There we go. So make the height y 7.5, and then there it is, from 2 to 6. So this box can't be any wider than 4 feet. So there we go. There's a word problem. Your actual homework for this, if you take a look at the blog here, is we're going to go back to, say, today's Tuesday. So page 392, same page that your other homework was on, but I'm adding some questions now. It's 10, 12, 19, 20. And then you can go to page 405 and do 1 to 4, 6, 13, and 14. And then you can jump to page 417 and do 4, 5, 8, and 11. I'll give you some work time tomorrow too, but for the most part, today is your work time for this assignment. All right, that's today's lesson.